Howdy, physics students. If you have seen my or anyone else's discussion about standing waves on strings, that stuff's pretty straightforward. Standing waves on strings are easy to visualize because you can see them when you hold a big long slinky between two people's hands and watch oscillations happen. But there is another primary system in which standing waves can be observed, and that is what's called an, well, so note up here, number one above this. Number one, strings. But number two, the other primary system in which standing waves can be readily observed are things called air columns. And an air column is a tube with air in it, right? And there are a couple of kinds of air columns, and we're going to start with one that we call open at both ends. And so quite literally, you just imagine a tube with no ends on it, no caps on the ends. Fair enough? All right, and when I say systems in which standing waves can be readily observed, what I really mean is, we're really talking about musical phenomena. Where else, why else, or in what other primary way do you observe standing waves? I don't know. Musical instrumentation is really the primary way. All right, so a lot of musical instruments are, in a kind of simplified way, tubes that are open on both ends. Particularly, we're talking about things like flutes and piccolos. They're open tubes. They have lots of fancy keys and stuff where you can change the length of the tube, but at their most basic, they are a tube with two open ends. All right. Now, in order to make a standing wave happen, something has to displace a system from equilibrium and ideally can keep driving that oscillation. All right. An oscillation happens and something's going to keep driving it. Now, when that happens, there's two separate phenomena that we really have to, to teach to the standards here. If you're an AP Physics, College Board wants you to know that there's these two different phenomena, and this makes teaching this sound pretty complicated. So this might get a little complicated, but it's the right physics. All right. So here's the deal. Let's imagine that there's this air column, and actually let's imagine a different air column. Let's imagine this is a guy at Penn State. His name is Dan Russell. He made this page, and if you read this, which I really, really recommend, he goes through and says, people kind of do a crap job of teaching standing waves and air columns. And I think I did a crap job for some time, and this has helped me develop a much better understanding of what's happening. So what I want to kind of jump right to, and I really, really recommend that you read this stuff, all right? But what I want to jump to is this animation here that shows physically what's happening inside an air column. Now, this air column is not open at both ends. This is quite literally like a cap on the end of an air column. All right, and over here, this oscillator is something that's driving the oscillation of air particles. All right, and so what you got to look at is a couple of different positions and a couple of different things that are happening. All right, so let's say we look at this particle of air here, that red one. All right, what you notice is that air particle is moving back and forth a lot, right? There is some equilibrium position around which it oscillates, and it seems like it gets from about here to about there, right? So there's an equilibrium position that it has that's about here, okay? And that particle moves a lot about that equilibrium position. Or if we look at that particle's displacement from equilibrium, so this means equilibrium position. Well, this place in the air column has lots of particle motion relative to equilibrium position. Yeah? But if you look at this place here, that particle doesn't move at all, and none of the particles along this line move at all relative to their equilibrium position. And so this is what's called a displacement node. There is no oscillation in particle position as a function of time. All right, here, everything along this line oscillates a lot relative to equilibrium position. So this is a displacement antinode. What I'm assuming is that you know what the difference is between a node and an antinode. Right? For a standing wave, these are the nodes, and these are the antinodes. Now, what's strange about this is that this other graph, and the print is real small here, but this is a graph of air pressure as a function of position. And air pressure is about not where things are, not where air particles are relative to their equilibrium position, but how much the air particles are squished together or spread apart. Squished together or spread apart. Squished together. So let's look here. Right? When we see this particle that doesn't move, right now it's squished, right now it's spread. Right now it's squished, right now it's spread. Right now it's squished. And we notice that oscillation in air pressure. Squished means high pressure. Lots of particles per unit volume means high pressure of air. Okay? And so when things squish together, high pressure. Spread apart, low pressure. Squish together a lot, high pressure. Spread apart, low pressure. And what we get is this interesting thing where at the same exact place where there's a node for particle displacement from equilibrium, there's an antinode for air pressure. And vice versa. All right. I like looking at the end here at this, at this walled off end, right? These particles can't move. A particle at the very end here can't move because, well, it's got nowhere to go this way. It can't be pushed through the wall. And it won't move this way because if it did, it would leave nothing behind it. Nothing's called a vacuum, and nature hates a vacuum. So those particles can't move at all, right? They don't displace at all from equilibrium. But what happens is the particles that are over here that are moving toward it, squish it, and then move this way, spread it. Move this way, squish it, move that way, spread it. So the air pressure at that location varies a lot. Another example of there's a node for one quantity as a function of time, there's an antinode for another. And you'll notice that at every location, when one thing is a node, the other is an antinode. Where one thing is an antinode, the other is a node. Now, I don't know if that makes things a whole lot clearer, but it sure is worth getting the physics right. And I've gotten it wrong a lot of times. All right. The big bottom line is that when we draw standing waves in air columns, we are always going to draw representations like this or like this. Because this is a, are you going to draw that? You're not. You're not going to draw it effectively. So we're not going to draw dots and how squished they are. We're going to draw graphs of, well, we're going to come up with a convention. We, in my class, we're going to draw this graph. We are going to focus on where our particles, how much our particles displaced relative to their equilibrium position. And we just have to know that where there's lots of displacement, there's not lots of pressure difference. And we have to know that where there's lots of pressure difference, there's not any change in position relative to equilibrium position. All right? There's a lot of science in that. All right? As a procedural matter, when we, solve problems with air columns and standing waves, it's going to come down to, a little more straightforward procedure stuff, but the science behind it is pretty darn deep. All right, so what's really happening in an air column? And I'm just referencing what we just saw. Two things are varying. All right, this might be air pressure, and we'll call this one particle displacement. Where air pressure, this doesn't mean zero air pressure and negative air pressure and positive air pressure. What it means is this is, maybe what we'll call 1 atmosphere of pressure. And pressure of the air in specific locations or at specific times is either more than typical atmospheric pressure or less than typical atmospheric pressure. All right, and then particle displacement is measured, from, well, really from each particle's equilibrium position. All right, so it really can be, you can have a negative displacement from equilibrium position or a positive displacement. All right, so here's the deal. Out here, out in all this region, that's just air. That's just a room. That's the rest of the world. And air pressure out here is 1 atmosphere. And air pressure out here is 1 atmosphere. That's a 1. And so that means that the air here at the very end of the tube basically is the air that's out here in the world. So that means that air pressure at the ends of these things is the same as air pressure in the space around it, and that's just 1 atmosphere. So there is not a variation in air pressure at either end of this tube. So now I'm going to say, look, here's a tube of length L. And we'll say this is, as a function of position, we've gotten out to length L. Well, at each position x is 0 and x is L, well, those are both places where the tube is open to the air and the air pressure is 1 atmosphere, and so the air pressure in the tube at the very end is also 1 atmosphere. All right, but what we need is a standing wave in here, so what we want is something that has, well, look, there's a node at each end, and so between that, in its simplest fundamental vibration, what we get is an antinode of air pressure in the middle, and you'll get an oscillation of air pressure in the tube that goes between way higher than normal in the middle and way lower than normal in the middle. But at the end there is no variation because, again, the air at the end is basically the air in the room, and the air in the room has that pressure. Okay? But, or conversely, in order to, and the bottom line is, how do we know there's a standing wave set up in an air column? The answer is because we hear it. The answer is because it makes some noise. You get a bottle of water with a little, little store-bought bottle of water, and you blow across the top of it, and it makes a sound. Well, it makes a sound because there's a standing wave that got set up in there. All right, and you observe that standing wave by hearing it. All right, and we hear sound when there's lots of displacement of air molecules. All right, so at each one of these ends, what we want is air molecules that are moving back and forth a lot relative to their equilibrium position. And so what we want is at position 0 and at position L, the ends of this tube, we want a big variation in position of particle relative to equilibrium. And we want a big variation at the other end also, where x equals L. So, and in the middle, right, where there's this pressure antinode, that means things are getting squished together a lot, moved apart a lot, squished together a lot, moved apart a lot. What we've seen on that last animation is that's a place where the particles themselves don't move. They get squished and spread apart, or it's attempted to be pulled apart, but they don't move. And so what we get is something that looks like that. And there's a variation in particle displacement that oscillates between, well, this thing has gone a bunch to this particle here at the very end has gone a bunch to the right, and maybe that's what this means. And then, a few instants later, it'll be displaced a bunch to the left. And so at some other instant, the particle's displacement as a function of position down the tube might look like that. So that's a lot to wrap your head around. It's a lot to wrap your head around, the fact that there is both a pressure variation and a displacement variation for individual air particles, and that those things are the opposite of each other. All right? What we will do in my class, and I think really in the majority of most physics discussion about this stuff, is we're going to focus on this. Whenever we draw standing waves, we're going to represent particle displacement from equilibrium as a function of position along the tube. Okay, I don't know if most texts are explicit about that or not, and Mr. 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 Russell seems to point out that people don't do a great job of being explicit about what they're representing when they draw these graphs. All right, but we're going to focus on. We're going to focus. Get back there. We're going to focus on particle displacement. All right, and so here's a tube that's open at both ends. I mean, it's the same thing we just drew, but I'm going to draw it again and talk about how we can characterize what I call the fundamental, or what is called the fundamental vibration for an air column that's open on both ends. All right, now remember, we're going to focus on the particle displacement thing. What we saw now, fundamental vibration. Fundamental vibration means lowest frequency. And it means that's the same as saying largest or highest wavelength. So what we saw on the last slide is at each end, this is a big key. Let's see, the criteria for a standing wave with an open end is there must be a displacement antinode at each open end. And that means we want the biggest wave we can find that has an antinode at each end, and that's a wave that looks like this. I don't love it. It's a wave that looks I don't love it. I'm picky. It's a wave that looks like that. That's better-ish. There's an oscillation of particle displacement where particles are either displaced a lot this way or a lot this way as a function of time. That's the open end of the tube, right? Here at the other open end of the tube, here's particles that are displaced a lot this way or a lot this way. And that's why we can hear that sound, because the particles are oscillating a lot. All right, super duper important to recognize here, folks. There is nothing, we're not saying that particles are down here and then particles are up here. We're not saying that at all. Particles are doing this. Sound is a longitudinal wave, right? When sound is going to travel this way, for example, it's because particles are oscillating this way. But it's a pain in the behind to try to draw that sort of oscillation we're not drawing all these dots of air particles. It's a huge pain. What we do is we turn this tube into a graph of particle displacement as a function of position. Okay? Now, like we said before, if this tube has a length L, here's a length L, we can, and you should, anytime you're doing any sort of solving, any sort of standing wave problem, you should relate the length of the medium string or air column to the wavelength of this oscillation, and that's a half of a wavelength. Fair enough? What you'll probably do from there is say, okay, that means that lambda is 2L, right? And then using an equation that talks about wave phenomena, specifically that the speed that the wave travels at is the product of frequency and wavelength, we could probably say, well, the frequency of this lowest vibration is V over lambda, or V over 2L. All right, this step is of huge importance. Make sure you do that. All right, when at all possible, draw the tube and draw the wave. Okay? So this says, you know, what is the lowest what's called resonant vibration in an air column? Well, that depends. It depends on, all right, the speed of sound in air. That's pretty relatively constant for most of the places we spend our time. It just depends on how long the tube is. And the longer the tube is, the bigger L is, the lower that fundamental frequency is. So that means long tube makes low frequency resonate. We'll hear a low frequency because the only standing wave that can be set up in an air column has to meet this criteria where it is of just exactly this size, where half of it will fit in the tube. The longer the tube is, the smaller that frequency, the lower the pitch. Yeah? It's okay? It's okay. Now, let's say that we have a bunch of tubes of length L. And remember, our criteria for a standing wave in an air column, well, is that there's a displacement antinode at each open end. And so there are other size waves that can fit in these tubes of length L that meet that criteria. Our fundamental one was we fit half of a wave from end to end, because that gives us antinode to antinode. Well, this one works too. It's the next shortest one. If I cut this thing in half and we go like this, we've now fit a whole wave in there. I'm not trying to say that this keeps going down to here. What I'm saying is this, I'll do it better, is that this is like the trough of that wave. And so now we've gone antinode to antinode, and there's an oscillation between that sort of particle position or particle displacement and that. And now we can say that here L is lambda, but I like to write it like this: 2 half wavelengths, the 2 being important to us. And then we could do a different oscillation where break this into thirds, and each one of these thirds we get a half of a wavelength. This can take some doing to draw these right. Well, this gives us, we've now in this tube of length L fit 3 half wavelengths. And guess what? If we broke this in half and then each one of those halves in half, if in each quarter of this we fit a half wavelength, then we can say there's an oscillation between that and this. We can say in this tube of length L, we've now fit 4 half wavelengths. For each of these, if we wanted to, which analytically you typically do want to, is say, well, this wavelength is, well, how about I'll write it, I'm going to do it like, it's odd to do it this way, but I'm going to. Why not just call it L? You'll see in a minute. Well, if V is F lambda, right, and F is V over lambda, we get that F is V over 2L over 2. If you didn't follow that, what I did is really this. 2L over 2, that's the same as 2 times V over 2L. And look, V over 2L, oh yeah, that was the fundamental frequency. This frequency is twice that. Move this, and this, and this. And so this frequency is twice F naught. I'll do that again for the last one down here. Look, so now this wavelength is 2L over 4. And if F is V over lambda, then F is V over 2L over 4. And that's 4 times V over 2L. And oh yeah, V over 2L was the fundamental frequency. So this is 4 times the fundamental. See a pattern? Guess what this one is? This one is 3 F naught. And these are called the harmonics, right? These are the harmonic numbers. So I'm going to say that, I'm going to write that here. So the second harmonic has a frequency that's twice the fundamental frequency. The third harmonic has a frequency that's 3 times the fundamental frequency. In general, the frequency of any harmonic, Fn, is integer n times the fundamental, just like waves on a string. Now, it's not always that easy. In the next video, you'll see that it's, well, not always that easy. But analytically, these things, these waves, these air columns that are open at both ends, analytically behave exactly like a string on which standing waves oscillate or resonate. Okay? So, again, this is a spicy meatball, right? There's a lot of science behind what ends up, in a lot of cases, analytically saying, can you draw this thing, right? It's important to know what this thing is that you're drawing, right? And how it's different from, fundamentally different from something else that's actually happening in the tube. All right, we're going to use a convention where we represent particle displacement at different positions along the tube. Okay? And then here's where the rubber meets the road when we get to solving some stuff. All right? All right, next video to come, we'll talk about a different system where there's an air column that's open only at one end. We'll close one end, quite literally, like put a cap on it or something like that, weld a piece of metal over the end. All right, but the other end's open. So that's coming soon. Okay? Thanks, folks. Adios.